Okay, good morning everyone. Today we will continue talking about some metal catalyzed reactions. You have basically learned a lot about palladium yet, all the most important reactions and processes, although there's a lot more in this area. The only question in my eyes which remains currently in the area of palladium and these cross-coupling reactions is if there will be ever a Nobel Prize for this. Because the Nobel Prize Committee, as you know, is awarding the Nobel Prize each year to a maximum of 3 scientists. I believe palladium cross-coupling reactions certainly deserve it, but the Nobel Prize Committee might have waited too long, because now there are so many major players in this field, and some of the original players like John Steele, as I told you, have deceased already, that it might become difficult to identify 3 people to award the Nobel Prize in this area. Now, the reactions I would like to introduce to you today were really only found, or had only found their way into synthesis in the middle of the 90s, and probably even only at the end of the 90s, people realized how much potential this has for synthesis. However, in this case, it took the Nobel Prize Committee only another 6 years, until the year of 2006, to award the Nobel Prize for a process which I would like to show you, and this is olefin metathesis. And the 3 gentlemen who received the Nobel Prize in 2006 were Robert Grubbs from Caltech University in the States, Richard Schrock, MIT, also in the US, and Yves Chauvin from France, who is already retired. Now, the basic process, which is really only already known since 30, 40 years, is the idea that you could have 2 alkenes and that these 2 alkenes, under the influence of a catalyst, can scramble the substituents. That was known, but it was for quite a time just regarded as a curiosity, and also there were not a lot of catalysts around which could do this, and certainly there were no catalysts around which chemists could easily handle in a lab, because very often they were extremely sensitive against moisture and air. The general type of catalyst which can do this process are certain metal carbene complexes. So this is a metal carbene. Where you have basically a metal, and then as the ligand which we have not seen so far but will be seeing a lot in the course of these 2 hours, is a carbene ligand. And I hope you remember carbenes as reactive intermediates in cycloproponations. Let me remind you maybe where you have seen carbenes in action. You can carry out cyclopropenations between an alkene, let's say isobutylene, and chloroform in the presence of a strong base, and then the chloroform is undergoing, under the influence of strong base and 1,1 elimination, is forming such a carbene intermediate. Which then can undergo 2+1 cycloaddition to form cyclopropanes. So this is where you should have seen carbene intermediates before, and we will talk a little bit more about carbene chemistry a little later after we introduce or after we talked about the metathesis. Now, carbenes are also very effective ligands. They make complexes with a huge variety of metals, and all these metal carbene catalysts very often are very reactive, and they do quite a number of different type of reactions. And one of the reactions is that they might catalyze the olefin metathesis. The three metals which can be used here are wolfram and molybdenum, and these are the developments which are associated or which were developed by the work of Professor Schrock. These catalysts are highly reactive, much more reactive than the ruthenium catalysts, which are the development of Professor Grubbs. However, the ruthenium catalysts are very tolerant against functional groups, and most importantly, the ruthenium catalysts are stable against oxygen and moisture. And the wolfram and molybdenum catalysts are not. The wolfram and molybdenum catalysts you have to handle in a glove box. And again, this is a technique, especially our inorganic colleagues know well, and usually they have glove boxes. Organic chemists do not have as a standard equipment glove boxes in their laboratories. So you can imagine that the ruthenium catalysts here really were the way to allow basically every chemist with standard organic lab equipment to carry out such ring closing metatheses. Now, the contribution of Carbene was that he postulated a mechanism early on which explained, he postulated this mechanism, I believe, already in the 70s, which explained the overall process. And then these type of developments, especially the ruthenium catalyst, only became in the beginning of the 90s, and the commercial available catalyst, which everybody is using today, only came around 1995, 1996. And as I told you, the Nobel Prize was awarded in 2006, which simply shows you how fundamental this development was. And I believe you will see in a moment when I show you some examples how this reaction is being used, that indeed it has created a completely new way to think about the synthesis of complex molecules. So let's start with the mechanism. How could this type of reaction work? And in fact, it is relatively easy, and let me show this to you on one process which is especially often used, and this is an intramolecular metathesis reaction, because, and there you see the first very useful application, because it creates rings. And let me just use a very simple, and I introduced the actual catalyst to you a little bit later, let me just use a very simple writing here for the metal carbene complex. I'm not writing any additional ligands these complexes all have. And the way it can be understood that the reaction is proceeding, and there's broad evidence that this is actually the case, but as I told you, Chauvin already postulated this very early on, is that it is a sequence of 2+2 cycloaddition and cycloreversion reactions. So in the first step, you could imagine that such a 2+2 cycloaddition is taking place, followed by a cycloreversion with the extrusion of ethylene. And so you form now a new carbene complex where you basically have transferred the metal fragment to your substrate here and have chopped off half of the original alkene which has combined with your carbene ligand here. Now all these reactions, all these steps are reversible here. So you need to have a driving force in order that this reaction will proceed into one reaction. And in this example, I believe you can see the driving force between ethylene is a gas which will leave your reaction flask, and therefore here you shift the equilibrium into this reaction, into this direction by continuously expelling ethylene gas, which leaves the equilibrium, and you can even force this. Very often people run these type of metathesis reactions by bubbling nitrogen or argon through your reaction mixture in order to help that the ethylene is leaving as fast as possible. Yes?
Can you explain how the metal shift works from the last step?
Oh, I think I've just drawn it differently, right? So here, let me just, it's this, right? And I've just draw this, I've just shifted this, I've just, oh, no, you're right. Thank you. So the metal should be here. Thank you very much. Okay, so this is the right fragment here. And in the next step, the same mechanism happens again. So another 2+2 cycloaddition. Occurs forming such an intermediate and then in another cycloreversion you are creating your ring and you are regenerating the catalyst. And so now you see what you have done. If you have a substrate which has two terminal double bonds, by applying a metathesis catalyst to it, you are able to form a ring here. So therefore, the process I've shown you here is a ring closing metathesis. And the beauty here is that you can form rings of just about, I'm tempted to say just about any size. So clearly 5, 6, 7 ring sizes which you very commonly encounter in natural products are being formed here. But also rings with greater than 10 membered rings up to very large rings have been formed, 10 to 20. The only rings which make trouble in any type of ring closing reaction, in intramolecular ring closing reactions, are the medium-sized rings, like 8, 9, 10, because that's entropically very unfavorable, and therefore the intermolecular dimerization processes compete. So that is also true for the ring closing metathesis, but there have been both with small rings, but especially also with large rings, there have been extremely good successes to actually form such, to do such cyclizations as well. And if you think about this, how general that process seems to be, usually we think about 6-membered rings, we think about Diels-Alder reactions, maybe 5-membered rings. We will see in one of the next next lectures how you can apply radical chemistry in order to create 5-membered rings. 7-membered rings, you probably would not have offhand a method to make specifically this type of ring size. But with this process, you can very easily do this. Let me show you an example. How this can be worked. But let me first show you actual catalysts which have been developed which show this type of reactivity. As I told you, the best type of catalysts people like to use because they are very stable and group tolerant are ruthenium catalysts. These ruthenium catalysts bear a carbene ligand. Since in principle, you might wonder why there is a phenyl group. In principle, these type of these type of carbene complexes can be synthesized by using an appropriate ruthenium precursor and decomposing a diazo compound, which will make the carbene, which is then trapped by the metal, and it has simply proven to be most easily to use phenyl diazomethane in order to bring into this carbene ligand here. And so the actual catalyst which was devised was a catalyst which looked like this. It's a ruthenium dichloro catalyst. So this is the reason why the oxidation number here is +2. two anionic ligands, and all these three ligands, the carbene ligand and the two phosphine ligands, are neutral ligands. And so here it was found that that these tricyclohexyl phosphine ligands were very good for these type of processes because they were very good electron-rich donors here, and this gave stable but also reactive catalysts for this type of processes. This is the so-called GRUBS1 catalyst. And again, especially now, since you're not doing metathesis reactions every day, certainly not something to remember on an everyday basis. But there is a second very similar catalyst, which is, however, a lot more reactive, where people have found that if you exchange one of the tricyclohexyl ligands for another ligand, which is again a carbene ligand. It's a so-called nucleophilic carbene. Again, this is a discovery which was made only recently during the last 20 years, that there are indeed carbenes which are stable enough that they can be isolated and basically stored. And again, also these type of carbenes are very good sigma donors, extremely good ligands. These are contributions Professor Hermann from the Technical University of Munich realized early on, that again, such carbenes, such nucleophilic carbenes are excellent ligands for metals as well. And it turns out if you exchange one of the phosphine ligands against one of these carbene ligands, you get an even more reactive type of catalysts. And so these two are now both commercially available and probably the most common type of ligands being applied. Ruthenium is a metal which is, of course, a precious metal, but it is by far better available than metals like rhodium or gold or some others which one might need. And also, of course, if you do this on an industrial scale, and metathesis catalysts are now applied in pharmaceutical synthesis in multi-kilogram scale quantities, you can, of course, recycle the ruthenium metal quite efficiently. So let me show you one example, how you can start thinking about how you can construct now rings very nicely and efficiently. Allow me to make an advertisement for my own group and show you the key step of a synthesis of a molecule which is called arglabine. which is this structure here. As you can see, this is a 5-7-5 membered ring system here. And the way we were able to build up the 7-membered ring here in the middle was by a ring closing metathesis. We had in hand such compounds, and now if you would not have available a ring closing metathesis reaction, you might think about how could you now create a 7-membered ring between these functionalities, and you would see that at least you would need quite a number of steps in order to do this. With the ring closing metathesis strategy in hand, this type of chemistry becomes relatively simple. What we did here is I'm actually missing another methyl group here. What we actually had to do is that we did an allyl reaction you have been introduced when we were talking about allyl catalyzed by a Lewis acid, boron trifluoride. This way, we are introducing the allyl group. You see now again why these allylations are also through the metathesis strategies are now an extremely valuable reaction, because easily, just about on any type of aldehyde or so, you can attach these allyl groups which now have a terminal double bond. We apply to it the Grubbs 2 catalyst. The downside here is that we had to use 15 mol% in order to do this reaction efficiently. This is usually not a catalyst quantity you would think that is efficient. What you would like to use is 0.1 mol% or even more. Usually ring closing metathesis, if you make 5-membered rings and not so highly substituted double bonds, just maybe a disubstituted double bond, you indeed get away with very low quantities of ring closing metathesis catalyst. What we are making here is we are making a 7-membered ring and a tetra-substituted double bond. This is still a very difficult thing, and the catalysts are not showing the activity we would have seen here. Nevertheless, the reaction works efficiently. You're creating the tetra-substituted double bond. I should have pointed out that although metathesis reactions are compatible with free hydroxyl groups, very often it is necessary, or reactions work better if you protect them. So this is also what we did here. But then, nevertheless, with about 90% yield, we were able now to close the ring. And you can see that it had not been too many steps now to finish the molecule. Everything was in place here. The tetra-substituted double bond was set up for epoxidation. The grooves we had chosen here were in a way that we could eliminate So actually the R1 was a methyl group here, so that we could introduce the double bond, and we had to desoxygenate here and introduce the exomethylene group. So relatively efficient, but certainly only possible by the ring closing metathesis approach. So this is one very common way to use metathesis. There are two other ones. So the first strategy we have seen was ring closing metathesis. And this is very often simply abbreviated as RCM, and also people, when you hear talks or lectures or so, people will simply talk of RCM, so keep that abbreviation in mind. There's the reverse strategy. You can do ring opening metathesis, and that is very often combined with a strategy or with a process of polymerization. So ring opening metathesis polymerization also abbreviated simply as a ROMP. This is quite a useful process to make polymers. And let me show you an example for this, how people can use this. Again, you need a driving force in order to do this. So typically, in order to drive a ring opening process, the driving force you apply is that you release strain. So for example, if you have a norbornene derivative, this is a strained alkene. If it somehow can open up this double bond here, you form a relatively unstrained cyclopentene. And so you can create, by applying now again, and let me just abbreviate the Grubbs catalyst here like this, you can create polymers. Let me just show you an example how this is actually being used. People have been using this to make polymer functional reagents. In the moment, since combinatorial chemistry in pharmaceutical industry is very important to make compounds fast and efficiently, there are two strategies to do this. Very often synthesis is carried out on the solid phase in order that you can remove all the byproducts by simple filtration. You have your substrates on the solid phase like you have learned in peptide chemistry. The alternative strategy is you do everything in solution, as you are more used in organic synthesis, but then you can use polymer reagents like a polymer bound carboxylic acid to remove base, a polymer bound amine to remove a carboxylic acid, and so on. And for this you need polymers which carry functional groups. And the ring opening metathesis is a good strategy to do this, because here you can make norbornene derivatives with various functional groups. For example, with the carboxylic acid, with amino groups, with phosphine groups, and so on. Many options. Norbornenes are accessible by Diels-Alder reactions between cyclopentadiene and then the appropriate alkene here. let me remind you of this, of the synthesis here. So cyclopentadiene and the appropriate alkene will give you these type of compounds. And now if you do the ring opening metathesis, you can see what is happening. Let's draw one intermediate here. So in the first step, you open up this this double bond here. So this should be the right intermediate, and creating now a new ruthenium carbene complex, which can react with your next norbornene derivative. And so this way, you can very nicely create polymers. Let me put it in here. Of these type of structures, where you have now made a compound which has a polymeric backbone, and basically you have any type of functionality embedded in here. And if you think about the alternatives in the you might have, in peptide synthesis, you might have learned about polystyrene polymers, which have then also, like the Wang resin, also have a chloromethyl group in there. Of course, also there you can introduce functional groups. However, here with this type of strategy, you have a lot more flexibility to very rapidly create basically any desired polymeric reagent here. So the fourth strategy one can think about is this cross metathesis, where you have in an intermolecular sense two alkenes which you would like to couple. Now, if these are the two same alkenes, the process is straightforward. And you can basically couple two of these alkenes together. However, if you are interested, which might be very often the case, to couple two different alkenes together, to form such type of structures, then there is, of course, a problem. The problem had not been there in the ring closing metathesis, because there simply the closeness of your reaction centers to make the ring has not been, or is not competing with intermolecular dimerization or so. But if you try to do two different type of alkenes here, then of course you have to prevent that at the same time the homocoupling can occur itself. So this is the undesired process. And this is here the desired way to do this. Now, one way you can do this is, oops, if one of your alkenes is very inexpensive and you can also easily remove then the byproduct, the homocoupling product, you might be able to use this in excess. And again, let me show you a strategy from our own group for this. We were interested to synthesize paraconic acids. And there are quite many of these are known, and they all differ in this R substituent here. And this R substituent, in principle, is a long alkyl chain. So this might be here chain C10, C12, C14, long type of different chains. Some of these have functionalities in here. The common precursor we had in hand to do such reactions had been this allylated butyrolactone. And now, of course, the idea is, I believe, obvious that you could use this allyl group as a handle to now introduce just about any type of chain. So if we wanted to have a C10 chain here, we have already 3 carbons in here. In the metathesis, we are losing 2 carbons because we are extruding ethylene. So what we needed in order to come to C10 is that we needed 9, right? We needed 9 atoms. So we needed 1, 2, 3, 4, 5, 6, 7, 8, 9. We needed this alkene here. And then in the ring, in the cross metathesis, chopping up these 2. Should then give you the desired or one of the compounds we have been interested in. And we should have the double bond 1, 2 here. And then you can imagine if it's just a normal alkene chain, you can do a hydrogenation. It actually turns out that these ruthenium metathesis catalysts are also active for hydrogenation. So if you don't want the double bond here, what you can do is, without working a reaction mixture up, you can just put on a balloon of hydrogen and hydrogenate the double bond away. One thing I should point out here is that in these type of reactions, you get easy isomers. We have not really talked about here in the ring closing metathesis. If the ring only allows you one double bond, of course you will then only get one, but in such an intermolecular process, easy mixtures are quite common, and so therefore very often you have to do the hydrogenation anyhow. So it turned out all we had to do here is use a moderate excess of this alkene. We've been using 1.5 equivalents because it turned out that the dimerization of this, because of steric hindrance, is not really such a competing process. So with a little bit of excess here, we got a way to do this reaction quite efficiently. And you see the homocoupling of this compound here is actually an unpolar. It's like a petrol ether, right? It's like hexane or so. It's a completely unpolar molecule we are forming here. So this was easily to be removed. So this might be a strategy if you have the luxury to say, okay, you use one in excess because it's inexpensive. The byproduct will be no problem for removing it. So then that is okay. But very often this is not your typical situation. So let's look into this a little bit more carefully, what type of requirements you have in order to do a successful cross-metathesis reaction. So let's look at this again. Let's look at the cross-metathesis processes again. What we would like to do is we would like to have two alkenes to be coupled with each other. So this one I will call A. This one I will call B. And so A plus A gives the undesired homocoupling product. B plus B gives the undesired other homocoupling product. And A plus B is what we want. This gives us the cross-coupling product. Now let's look at rates. And I think you will immediately agree that what would be nice is this is slow, and this is fast, right? If we would be in that situation, we would be all set. However, this is not the normal situation, because if let's say one of these alkenes is not reactive, not very reactive for metathesis, then each of these processes which will involve this alkene will be slow, right? And so if, let's say, if B is slow for metathesis reactions, then this will be slow. But you would expect that this is probably also relatively slow, and then that this would be the fast one. And so this scenario which I have drawn, which I've given you, is not a likely one. That the reactivity is that only if the two are matching each other, that this is the way it is. However, it turns out that indeed it is enough if one of the alkenes is reacting slowly. So even if you are in the situation that your homocoupling, the first one, is fast, because your alkene A is a very reactive one, and it will just react with any type of alkene. And this second process can be slow. The third, and then let's say your alkene B is very unreactive, so everything which involves B is a slow process. This will, interestingly, this scenario will still lead to the cross-metathesis reaction as long as your reactions are reversible. So this is a very important message here, that in principle, of course, also an alkene like this can undergo, with your Grubbs catalyst or with any metathesis catalyst, can do the reverse reaction. And can, basically, the catalyst can split this again and form, so for example, if this now reacts with your carbene catalyst, of course, this can simply react back. And now the trick is, look at this. If we do this first step here, if we do the homocoupling, in this moment, of course, we have extruded ethylene. And we do this in any type of these reactions. Ethylene is being removed. But now you might see if you start forming only, if you start only forming the homocoupled products, let me put this other way. If you're forming now the one homocoupled product very fast, and this product is not doing anything here, by now reacting back to this one and regenerating here your first, you're regenerating your alkene, and now reacting with the second slowly reacting alkene here, you will shoot out another molecule of ethylene. And this starts driving the reaction here, that by consuming this reagent with this alkene here, in the cross-metathesis reaction, you will also generate basically the ethylene coming out by reacting this. And therefore, although this is faster than this process, eventually this carbene will then react here and will generate another molecule of ethylene, which then allows you to form the cross-metathesis product. And so therefore, cross-metathesis reactions work usually quite nicely if you have one alkene which has like an aromatic group or an alkyl group. And if then you have one one alkene which is electron withdrawing, like an acrylate. And then if you allow the reactions to go sufficiently long, you will generate exclusively the cross-metathesis reactions, because again, this one will react fast, it will pick up the ruthenium catalyst all the time. This one will basically undergo very slow reactions, and nevertheless, only if this is also reacting, we chop off the 1/2 in ethylene which we need here. And so eventually, this will then also be consumed and undergo the reaction with the more reactive metal carbene here. So cross-metathesis is also now without the need of using excess of an alkene of one coupling partner. If you have one unreactive one, it's enough to drive the reaction, and you will not form, and this is the important message, you will not form the homocoupling product of your faster reacting alkene. Okay, I have given you quite a number of examples where the normal olefin metathesis is applied. Now let's look at another type of metathesis reactions. Why does the cross-coupling product, say again?
Why does the cross-coupling product do not undergo the reaction with the catalyst anymore? The R1 does undergo the reaction with the catalyst, but A plus B doesn't.
It does, of course, as well. So if you have this, then your cross-coupled product, let's say hopefully you have 100%. And then you have your ruthenium fragment, your catalyst, and let's hope you have it only in 1% there. Then, of course, the equilibrium is still there, but the only way this can react back is always to the product, right? So whatever, when you start making exchanges, it cannot do really anything. Yeah. And but also keep in mind, so this is now also, this is the slow, that's the slow reacting part, right? So again, also this is not very reactive. Okay, so let's look at this again. Now your question, of course, is valid. So this is the fast process, right? So this was fast. But everything where R2 is involved is slow. So for example, this I should. Okay, now let's look at this carefully again. We're extruding ethylene here, right? So if this is reacting back, so we have the ruthenium so if you have this, which if it reacts with remaining catalyst, we will be forming this, right? And this is, let's say this is fast here. And then we have this reaction here, which has the slower reacting alkene in here. So this is slow. And it will form the alkene plus ethylene in this case again, because this is, or we have already the ruthenium fragment here. So wait a minute, somewhere we should lose one equivalent of, somewhere we should lose one molecule of ethylene here. So we're reacting this back. So we're creating this, we are reacting this plus this, so we are creating this plus the ruthenium, which has now a terminal CH2 group. And if this is now reacting with our fast reacting alkene, then we're forming ethylene here. So let's look at this again. So this is fast going back and forth. This is slow. And now this one here will react fast with our initial alkene here, right? So the back reaction here, so this will eventually react, but then the remaining, this carbene fragment, if this now reacts with this one, you create another molecule of ethylene, which leaves the equilibrium. And then again, you have this ruthenium fragment, which can be in equilibrium with this homocoupled product, and this can go back and forth, but only when it starts reacting with a slower one, you drive the pathway by generating another molecule of ethylene. You cannot do this by simply doing this. And again, you're right. This could, in principle, could react back here too. Then you are in the equilibrium. But eventually, shifting the equilibrium will only succeed if you react with another molecule of this one here, right? Because then you're driving out ethylene. And so ultimately, it's the ethylene extrusion which drives the reaction. And the trick is that the slow reacting alkene will not react with itself. So there is no ethylene coming from this process. The process where you generate ethylene will only come from reacting the fast reacting alkene with itself and reacting then ultimately the fast reacting with the slower reacting alkene with itself, because this will then in this process I've shown you generate the molecule of ethylene here. Let's look at one of these examples probably again in a tutorial, and let's see if we can believe this. And so what I said here basically has nothing to do. It's just simply that this process is generally slow, so the reversal here will not easily take place. Only you're simply consuming a faster reacting alkene rather than doing this back reaction. So what about triple bonds? And also this is possible. And for triple bonds, also especially the shock catalysts, which I haven't shown you yet, are especially effective. And let me just show you one example how one of these molybdenum catalysts looks. So again, you see the similarity to the ruthenium. Also, the molybdenum catalysts have a carbene ligand, and you can, therefore, if you think about the mechanism, it's completely analogous to the ruthenium catalysts. Then as a second ligand, you find such iminium ligands here. And then you have usually two alcohol ligands here as well. And so these type of catalysts work analogously. However, they are to the ruthenium catalyst, they are more reactive even, but they are less functional group tolerant, and they are very air and moisture sensitive. But let's look at the case, what happens if we have a triple bond involved in such a metathesis reaction. And again, let's choose a ring closing metathesis here. And so we think about this in the mechanism in the very same way. Usually the triple bonds as a place of a higher electron density will react here, and you form again such a metal cyclobutene in this case. And now if you do the cycloreversion, what you will create here is you will form your metal carbene. However, note that on this position here now, you have added on the one end of your triple bond, you have added another carbon, which has now become a double bond here. And so now this metal carbene can, if it would undergo metathesis reaction here, then it would simply react back. If it undergoes metathesis reaction with the double bond over here, then it will form the ring closing metathesis here. To form such an intermediate. And now if this will undergo cycloreversion, you will create your ring-closed metathesis product. However, now as you can deduce from the reaction mechanism, this carbon here is this carbon here, and it has taken basically has taken the carbon from the carbene here, from the carbene catalyst, which of course now as we're generating back the carbene catalyst here, let me give this another color, if I would have one. This carbon here, we don't want to mix this with the radical here. But this carbon is ending up here, and basically this carbon is now in the catalyst cycle being regenerated in the catalyst. But if you want to look at this formally, then actually this carbon has ended up here, right? So you're not shooting out in this case, there's no loss of ethylene. It's a scrambling of the two halves, where basically half of this alkene group here has been added, has been moved over to your former double bond here. Now this is very useful because the functionality beside the ring you're creating here is a 1,3-diene. So the alkene alkyne metathesis is then ultimately creating a 1,3-diene here. And this is, of course, a very useful synton for Diels-Alder reactions. And now I guess what remains to be asked is the question, can we do even alkyne-alkyne metathesis? And for this, try to formulate a reaction with such a metal carbene catalyst. You will see that this is not leading too far, but people have found that you can actually do the scrambling if you don't have carbene complexes, but if you have metal alkylidene complexes. Let's see. And then you can also this way generate such reactions as I've shown here. It's not quite as common. For example, in the ring closing case, you can see immediately you need a pretty large ring so that this would be successful. Nevertheless, again, these type of reactions have been developed now as well, and we can look maybe in the tutorial as a typical on typical reaction mechanisms. You can try to see if you can formulate a similar mechanism with such an alkylidene complex as it's being done with the carbene complexes. So with this, I believe I will stop here for today. I hope you will take this metathesis strategies in mind. If you look now at rings, you might look in a very different way rather than, let's say, Diels-Alder reactions or other ring closing strategies you have known here. And so I hope you see that this is a very good, very powerful tool in organic synthesis. Okay, with this, next Friday, tutorium, next Monday, also tutorium, and we will have the next lecture on Tuesday. Thanks.